really a great pleasure to be back here in Northfield. Yeah, well, you heard the story of it from Dr. Kane. I do want to say, usually when I give a lecture, I like to just have it in front of me and talk through it. But I can't really do that this time because I haven't had a chance to, to review it well enough. Also, it's not super up to date. Luckily, this topic doesn't have to be greatly up to date. This version goes back to 2016 because I was just asked to look through my computer or my files and find something that would work. So this is what I decided to talk to you about. I don't think, if there's a number or two that may have been revised since then, but I think in essence it doesn't matter that it was written almost 10 years ago. The original title was Some Questions About Space and Time in Modern Cosmology. So you'll see that I have questions, I have suggested answers. Some of them I'm more confident of than others. Some concerning time particularly, I think it's very speculative. So we'll see what you think. I look forward to having a discussion with you afterwards. Okay, so here we go. I believe that there can and should be a friendly conversation between natural philosophy and the specialized sciences. It is with this in mind that I set out to write this paper about modern cosmology. In particular, I thought it would be worthwhile to ask some very simple questions about space, time, and motion as they are conceived in modern cosmology. By simple, I mean questions that may and do occur to non-professional readers of modern expositions of the subject. It does not follow that these questions will have simple answers. These questions tend to touch upon fundamental matters, and these are often difficult to address in a simple manner. How exactly, for example, are we to understand Euclid's account of why two triangles having two sides in the included angle equal are congruent? To think about this, issues prior to the science of geometry have to be considered. Similarly, cosmological answers to questions about space and time will involve us in prior considerations. And these prior considerations fall under the scope of the natural philosopher. One source of difficulty in addressing these questions is that the words used by cosmologists may have meanings unfamiliar to the questioner, despite the familiarity of the word itself. The name space is a good example of this. Others have an appreciation that may be familiar, but which may not come to mind when the layperson hears the word. Expansion, as applied to the cosmos, is an example of this. Other names are seemingly well understood until one tries to give an account of them. Time is a notorious example of such a name. You may remember that St. Augustine says, "I know what time is until somebody asks me to explain it." So one aim of this paper is to explain the signification of these names in modern cosmology. Another difficulty is that there is not a consensus among experts about the most likely answers to some of these questions. Different opinions about and interpretations of more fundamental parts of physics, which are presupposed by cosmology, both general relativity and quantum mechanics, make it impossible to be satisfied with the answers currently given to many of these questions, as judged from within physics as a whole. This should bring home to us the truth that the most general questions about the nature of the physical world, its constitution, its origin and destiny, fall under natural philosophy and cannot be satisfactorily answered from within any specialized science, especially one whose method makes use of artifacts such as mathematical models. The fact that these models and even the more basic theoretical structures which surround them undergo change from time to time shows the need for a more certain science, one which is capable of judging the principles of the more specialized sciences and of offering critiques of their conclusions in light of more general considerations. This task belongs to natural philosophy. I will try to make a very small contribution to such an examination and critique by offering a dialectical consideration of the notions of space, time, and cosmic expansion as they are understood by contemporary cosmologists. By cosmology, I mean the branch of astrophysics that attempts to understand the nature, laws, and motions of the universe considered as a whole, in terms of received physical principles. The basic outline of cosmology, as it is understood today, rose from two very different sources. One was the attempt by mathematicians to work out the cosmic implications of the general theory of relativity, and the discovery by astronomers of the recessional motions of the galaxies. I'll say more about that. These two developments converged to produce a new conception of the cosmos as different from that of the scientific revolution as the Newtonian concept of the universe was different from the cosmos of the ancients. In one important respect, however, the new cosmology marks a return to the ancient conception, however different it may be in most ways. The most striking feature of contemporary cosmology is the recovery of the cosmos itself. I'd like to give a brief account of how this came about. Post-Copernican thinkers assumed that the universe had only the unity of a heap. Newtonian dynamics was considered adequate to explain all the motions of celestial objects, as well as the processes by which they could form under the influence of gravity. The universe was seen to be a vast, if not infinite, expanse of void space in which stars are scattered around like molecules in a gas. For a long time, it was thought that the Milky Way was the entire universe. Although some early followers of Newton envisioned an infinite universe filled more or less uniformly with stars, Newtonian dynamics prohibit such a scenario. As Einstein expresses it, Newton's theory, quote, requires that the universe should have a kind of center in which the density of stars is a maximum, and that as we proceed outward from the center, the density of the stars should diminish, until finally at greater distances it is succeeded by an infinite region of emptiness. The universe ought to be an infinite island in an infinite ocean of space, end quote. The reason is that if there were an average finite density of mass throughout an infinite cosmos, the intensity of the gravitational field would everywhere be infinite itself, and that's absurd. At least Newton took it as absurd. So given Einstein, I think Newton did too. Given a finite amount of matter then, its eventual concentration towards the center would come about through the mutual gravitation of the parts. Moreover, according to the Olberg paradox, the night sky ought to be luminous in every direction if there is a more or less uniform distribution of stars throughout infinite space. Although both problems could be solved by making ad hoc assumptions, most astronomers saw no reason to do so. For these reasons, it seemed reasonable to most astronomers to hold that the Milky Way was the cosmos. But in the early years of the 20th century, some began to speculate that certain of the faint nebula visible through telescopes were island universes in their own right, collections of stars comparable to the Milky Way. The issue could be settled by finding out how far away from us they are and whether they formed a coherent system sharing a common motion. Okay, so now I'm going to talk about how you get some sense of how far away the galaxies are. Okay, so we're going to make an analogy first. Think about a sound that falls in pitch when it arrives from a source moving towards us due to a lengthening of the wavelength. That's the Doppler effect. So police siren, let's say, you hear it coming towards you. You hear an increase in pitch when it comes towards you and a decrease in pitch as it goes away from you. Similarly, there's a shift to the red of light, the red side of light coming to us from any source moving away from us. We can measure these shifts in the light coming from the stars and other celestial objects. Sometimes the shift towards longer wavelengths are observed, sometimes shifts towards shorter ones. According to the most obvious interpretation of these observations, some celestial objects are moving towards us, some are moving away. These observations indicate only the component of motion that's directly towards your way. So which one did you think we put here? There it is. That illustrates, it's not a very clear diagram, but it illustrates spectral lines. When you study light, we'll look at these maybe, and how they can be compared in how they're shifted relative to spectra that are measured in the laboratory on Earth. So that's the raw data. So making use of the best data he had available for galactic distances, Edwin Hubble found that more distant galaxies, ones therefore seen further back into the past, have larger redshifts than nearer galaxies. And the relationship more or less proved to be linear. In other words, he found that there was a proportionality between the redshift and in other words, the velocity and the distance of the galaxy. So I'm going to show you just a couple of slides showing that. There we go. This diagram essentially is plotting, there we go, redshift versus distance. So the redshift is increasing by distance. You can see there's a lot of scatter in the diagram. That's because these are objects fairly close to us, and you have proper motion. Besides the general trend, there would be motions of something towards us in some way and so on. So when you looked at the data by consolidating larger regions of space and doing it sort of averages, then you got a diagram more like this. So you can see a fairly tight line there indicating a proportion between the redshift and the distance. So this was convincing to everyone. There we go. Most of modern cosmology rests on attempts to explain in as much detail as possible the systematic relation between distances and redshifts. More extensive and more precise measurements that have come from the Hubble and the Planck Space Telescopes, probably the James Webb now, have complicated the picture by showing departures from the simple linear function that I just showed you. And on this new evidence, we started getting these new ideas of what they call cosmic inflation. The idea that there was a rapid increase in size of the universe in a small fraction of the section at the beginning. And also the idea of dark energy, and we'll say more about that. But that's basically the idea that the rate of expansion is increasing due to some mysterious input of new energy into the cosmos. But it's worth repeating. The raw data that we have links redshifts and apparent brightnesses of celestial objects, indicating their distances. Everything else is just an attempt to interpret these measurements, to try to see how they can be explained. So far, I've spoken as if the redshifts indicated recessional velocities in a literal sense, just as the falling pitch of a police siren indicates that the patrol car is moving away from you, and so you're safe from being pulled over. But this is not how the cosmologists interpreted the redshifts, even in Hubble's day. The expansion of the universe is not to be thought of as analogous to the expansion of a mob of people as they leave a club or ballpark into which they've been crowded. Such an expansion is not, of course, a motion, but it's rather an increasing of a boundary and closing all the moving people. You have people moving away, then it's increasing the boundary, right? The individual people are moving. Such a boundary is an artificial construct which may be useful in various ways, but does not itself have a physical meaning. Now, the forces at work in causing such a peroxidase expansion of a boundary and closing the galaxies would be those of Newtonian dynamics. Some sort of originating outward push and the subsequent inertial motion of the galaxy. So as if something happened at the beginning that sort of pushed them away from each other, that's one picture that you might have of this. But there are a number of difficulties with this kind of explanation of the phenomenon. If the galaxies formed prior to expansion, what natural cause could possibly result in them flying apart from each other like so many projectiles, while maintaining their beautiful internal symmetry? So explosions tend to tear things apart, right? So what would have pushed them away from each other without messing them up? The required coordinated pushes on the individual stars and particles of dust and gas that constitute the galaxies would require a sort of choreography unimaginable from the point of view of created nature. Granted that God could cause this, but that natural causes could do it is beyond belief. That the universe originally consisted of a symmetric collection of uniform particles that somehow acquired an outward movement and then later coalesced into stars and galaxies, that's not far-fetched. But even this account turns out to have serious technical difficulties. And it's more reasonable to think that the unity of the effect points to a unity of the underlying subject. In other words, there's one expansion, there ought to be one thing that's expanding, right? If we accept the evidence that Hubble's constant is increasing with time, like the dark energy idea, then the Newtonian explanation is completely destroyed. Okay. So, we're left with this idea that the cosmos is a unified thing that is undergoing growth or something similar to growth. We naturally wonder what it is and how it is unified. It's interesting to note that this new conception of the universe as a cosmos was developing even before the relativity theory was proposed by Einstein. You had the notion with Maxwell and others of a luminiferous ether pervading all space, filled with electromagnetic radiation, and that idea became common in the 19th century. So already people were starting to have the idea that maybe space was something, not nothing. Okay. So let's go back to the Hubble diagrams, the one that showed that linear relation. The standard explanation of the Hubble diagrams given by Einstein's theory of relativity is simple and elegant. What we measure is that the wavelength of light increases in proportion to the distance the light has traveled. Okay, so the farther away the galaxy is, the more redshifted it is. There's no need to suppose that the galaxies are themselves mobile, because it is sufficient to assume that the space through which the light is traveling is itself growing. If I were to draw a wave, sort of a wave shape representing light on a piece of rubber sheeting, grasp it at both ends and pull it apart at a uniform rate, the distance between the successive crests would steadily increase, right? And that's like the relativistic account, in which, in essence, is that light from distant galaxies travels through space, then is becoming more and more extended as time goes on. The longer the light travels, the more its exposure to this expansion, and the more redshift we observe. Okay. So this is an interesting idea, and it has some nice consequences. First of all, the fact that you have a finite speed of light provides us an opportunity and a difficulty. Think about this. Because light is not instantaneous, we have to distinguish between our picture of the universe, what our instruments reveal, and what has been called a map of the universe at a given time. So in other words, we're not seeing everything at the same time, right? So we want to distinguish what we actually observe from something that would be like God's view, where we see everything as it is simultaneously. That again has been called a map of the universe. And what we want to know is how the map itself changes with time. This latter, the map as a function of time, is really what the cosmological models purport to describe. I hope that makes sense. So it's a mental construct, again, because we can't directly observe it. But we now see why the finite speed of light is advantageous for our knowledge. If we were not able to look back in time, as we look outward in space, we would have no way to know how the map is changing, except by observing the universe over many, many, many millennia, which we don't have time to do. Okay. So, does that make sense? So as you look further back, you're looking into the past, so you get like sections of the universe as it was in earlier times. I want to examine in a little more detail this notion of a map. Like a road map, it locates key features of the landscape, or I should say the skyscape, I guess, relative to each other and indicates how they're connected. Like a topographic map, it abstracts from most of the features of the landscape to give an overview of the terrain. But unlike these familiar maps, it exists in algebraic form rather than as a picture. And in this way, it's more like the GIS data that cartographers use to produce their map. Our map, then, of the cosmos is a mathematical model describing cross-sections of the cosmos as it exists at various times. Before we go on, we want to consider what version of the universe is being mapped. Because there's a distinction in the meaning of universe that the cosmologists make in their own thought, but it's usually not mentioned in the popular literature. They distinguish between the universe considered under three aspects. First, there's the whole universe, which is the entirety of physical reality. Next, there is the observable universe. This is the universe as it is in principle observable by a given observer. So in other words, with the finite speed of light, we can only look out so far, right? So anything that's too far away to have had time to get to our eyes, we can't see it. So the observable universe includes just what we can, in principle, observe. Okay. Finally, there is the actually visible universe, the universe insofar as we're able to observe it in fact with our instruments. So we think that in principle it would be observable further out than we can actually see it with our instruments, at least as of the time I wrote this paper. This universe may also be thought of as a sphere, right? Because it's a sphere of a distance out to which we can actually see the light coming towards us. Whatever we say about the observable universe is an extrapolation from what is known or conjectured about the actually visible universe. And as to the whole universe, that is what the mathematical models deal with. So we're looking, in the mathematical model, we're trying to go out beyond what even is in principle observable to us right now. The various cosmological models which you read about describe different possibilities for the whole universe. Any judgments between the possibilities have to be made, though, on the basis of what we have in the visible universe, because that's all we have to go on. So we have to begin our considerations by what we can actually observe. And then extrapolate from that to what we think is going on in the whole thing. Now that we know what is being mapped, that is, the whole universe, we must consider the elements of the map. First, we must see what is meant by space, and then by time. Finally, since the map is always changing, as the universe is evolving in some way, we must consider how we ought to understand the claim that the universe is expanding. Because that's the claim that they make on the basis of the Hubble law. That the universe is expanding. I've already explained, it's not that the galaxies are moving away from each other with local motion, but rather that space carrying them along with it is expanding. Okay, so we have to think more about what that would mean. Okay, let's start with space. It's a commonplace that the universe consists mostly of space. But what is space? I think we can distinguish three approaches to this question. The first is that of the common man, which is also that of the natural philosopher. The second is that of the pure mathematician. And the third is that of the physicist, which is also that of the cosmologist. And that's a kind of mean between the other two views. And I'll try to describe them briefly in order. The idea of space, so this is the space that appears to every person, the common man. The idea of space, as Einstein himself explains, arises from our experience of putting boxes inside of boxes. From this it is clear that the concept of place precedes the notion of space. So we think there's space in this box because I can put another box inside it, right? But prior to the notion of place is the notion of being extended, that is, of having part outside of part. Experience shows us that there are three independent extensions, height, depth, and breadth, right? And bodily substances must have all three of these, which are commonly called length, breadth, and depth. And without body, we would not have space. The space considered naturally has three dimensions, right? The common man, if he thinks of this space at all, imagines it as a sort of empty room in which things exist and move about, right? The natural philosopher, naturally enough, has some questions about this. Is space something really distinct from body? Does it have natural limits? Is it immobile? Why does body require three dimensions? Is it just a fact of experience that it's limited to three dimensions, or is it impossible there should be more? Some of those questions, at least, you'll be considering as you read Aristotle on place, right? But rather than try to answer these questions, as I say, these are some questions that come up. I'm not going to talk about all those. Rather than try to answer them, let's return now to the idea of the big empty box. Okay. We can think about the dimensions of the box in abstraction from the box, and so be led to the idea of a three-dimensional coordinate system, a la Descartes and others, right? To the pure mathematician, a space is an abstraction of this sort. But he does not stop at this abstraction. He goes on to construct more complicated objects using these abstractions. Through the setting aside of spatial images and extension and using the extension of the methods of algebra, it's easy to extend abstracted three-dimensional coordinate space to as many dimensions as we please. Each of these dimensions is conceived in exactly the same way as a continuum of numbers. The numbers may either be real or complex, or whatever kind of number he wants or needs. The various dimensions are related to each other by rules which the mathematician stipulates. So anyway, there are different things you can do there. So I hope that makes sense. I mean, that once he's abstracted the notion of dimension, there's nothing, and he doesn't worry about fitting it to any spatial imagery, any ordinary physical space. He can make as many of those as he wants. That's the pure mathematician. Now the physicist makes use of the mathematician's algebraic constructs, but they're obviously not sufficient for his purposes. To make a space physical, its dimensions must be related, at least in principle, to real physical measurements. They no longer need be dimensions in a univocal sense, nor need they be restricted to three. For example, classical mechanics uses what they call configuration spaces, in which some of the coordinates are measures of position and others are measures of momentum. So they're using the complicated mathematical structure, but they're relating everything to something measurable in nature. The description of a body freely moving in space thus requires 6 dependent variables, with time as the independent variable, right? Space of the physicist is like that of the common man in that he understands it in terms of physical realities, but he is like the mathematician in that he finds and uses an artful algebraic structure to relate these realities to each other. Okay, now, the space of the theory of relativity is what is known as a 4-dimensional manifold that is Euclidean on small scales. So just as, if we did a map of Northfield, we could put it on a flat piece of paper and not be very inaccurate, right? Because compared to the curvature of space, it's a very small area. So actually, that's the idea of pseudo-Riemannian manifold. I can use the fancy word for it. And that's the way theory of relativity thinks of space in the 4-dimensional continuum. In other words, he thinks it's really not Euclidean on larger scales, but as soon as you get to a small scale, you can treat it as Euclidean. That makes the mathematics much easier to do, right? Makes it even possible to do. So that's his way of conceptualizing it. The student of relativity, and he also likes to use the phrase space-time to describe the object of his study, because he is more inclined to think about this very elegant 4-dimensional description of the world that he has. The math is very nice. The cosmologist, on the other hand, as opposed to like the one doing the pure theory of relativity, is more inclined to keep space and time separate in his thought, maybe not always in his descriptions, but he often tends to do that in his thought. Perhaps because his scientific roots lie in astronomy, something a little more connected to the world of experience. So from here on, we're going to follow the cosmologist as well as common sense. I'm not going to talk about 4-dimensional space-time. We'll talk about space and time. Okay. So once again, what is space? It is certain that space is not a mechanical ether, the way Maxwell thought. And by this we mean it is not a substance possessing the ordinary properties of matter. It does not have mass, temperature, inertial resistance, etc. Space does not have those things. Space must not have any properties of its own that would impede the action of bodies or of radiation. That's experience, okay. Yet, it is not nothing, since it underlies many accidental properties. Besides containing radiation and ordinary matter, various fields exist throughout space. Besides the familiar gravitational and electromagnetic fields, we now have the Higgs field and no doubt other exotic ones, okay? The primary field, though, filling space, is the gravitational field. That's prior to all the others, okay? At least that's how it looks in the science nowadays, and I think it's true. This is a field sui generis. It's absolutely unlike any of the other fields. Others may be called fields of force, but gravitational field is not like that. Other fields also seem to exist in quanta, which you might have heard of, that you get kind of description, like photons and light. And maybe the gravitational field does too, but the truth about that is not known. There's no evidence about that yet. The theory of relativity proposes that its very nature, the very nature of gravity is to be a manifestation of the physical dimensionality of space and time. So it's tied to space and time themselves. It's not a field of force like the others. Okay. The conception of space as measured extension opens the door to geometries that are non-Euclidean in nature. The use of these geometries to describe the motions in the presence of strong gravitational fields has been very successful, and so this approach is useful to astrophysicists and even to rocket scientists, even to those who are launching these satellites that we use for communication. They take all this into account. The cosmologist, however, is not interested in the universe on a small scale. One of his principal tasks is to determine the geometry of space as a whole, that is, to determine its global gravitational field. Forget about all the local variations. In the standard cosmological model, space on the large scale is presumed to be homogeneous and isotropic. What does that mean? That's called the cosmological principle. One way of putting it is that there's nothing special about where we or anybody else is. It's the same everywhere in its properties, and it looks the same in every direction. That's, again, the cosmological principle. It's just taken as a principle. We don't have any proof of it. The background space, therefore, may be compared to a smooth equilibrium surface of the ocean. The presence of other beings produce ever-changing distortions of this field, this gravitational field, just as winds and boats create ever-changing ripples in the sea. But the level surface remains as a principle, even if there's nothing but waves going on in the ocean, right? The sea level is still a principle, right? And it's what you would see. So it is assumed by cosmologists that this space, like this, will be characterized at any given time by a simple and uniform geometry. That principle that I mentioned, the cosmological principle, demands that kind of simplicity. So either it's Euclidean or it has some overall specifiable non-Euclidean character. Okay. Now, the background of the geometry of the whole universe should, in principle, reveal itself in the visible universe, the one we can actually see. But what this data is telling us is not certain. Until recently, it seemed easy in principle to find out whether the universe has an overall curvature, though it's not so easy in practice. I don't know how much I want to go into detail about this. Maybe not too much. Basically, the idea is how much mass is there in the universe. So the idea was if there's enough mass to have closed space in on itself, you'll have a finite enclosed space. If there's not, it'll either be flat Euclidean or hyperbolic, like what you do with Lobachevsky with your singers. Okay. The idea that space is flat and therefore on average that's Euclidean is an appealing thought, right? At least to most of us. But in view of the fact that the claim is usually understood to be about the actually existing universe, but not about an abstract, and not merely about an abstract manifold, but the actual universe, it does raise some questions, right? If it is flat now, if it's flat in Euclidean, was it always flat? Does the flatness of the cosmos imply that it's infinite in extent? If not, what limits it? On the other hand, does it follow from having the universe begin with a Big Bang? That's the common idea, right? Does it follow from that it's finite, that it started out small and even point-like? I mean, I guess you've all heard of the Big Bang. Is that right? I guess I heard that's the idea. It was actually a Belgian, one of the first proponents of it was a Belgian priest, Father Lemaitre, very interesting person. He and Einstein knew each other. Anyway, the last of the questions, did it start out small or even point-like? That's most easily answered, since it's just a matter of examining the conception, I think. So what's meant by the Big Bang? All that's meant by the Big Bang is that if the cosmic expansion is traced back in time, one arrives at a beginning of motion in time, as well as the beginning of the universe, right? Everything. The Big Bang is called a singularity sometimes, in the sense that time and space are not defined for anything prior to it. Oh, like a singularity of the inflection point on the curve where, anyway. It is analogous, well here, it's analogous to a point which terminates a line. So the Big Bang would be like that. It would be analogous to a point terminating a finite line. Such a point is the beginning of a line, but it is not itself a line, right? Point. The Big Bang, therefore, is an event. It is not an extension, because it's a boundary of extension. In fact, since points do not actually exist, the initial universe, in fact, must have had extension in all three dimensions, which means it really wasn't a point, right? It's something very small. The Big Bang, as such, is not inconsistent. That idea is not inconsistent with the idea of an infinite universe, by the way, although it seems strange. Though that would imply that the universe has no size. If it's infinite, it has no size, right? And therefore it can't go any larger. So if you think that, there's some interpretations of cosmic expansion you couldn't have, which didn't really make sense of it. But neither does a flat universe, having a Euclidean-like way of being measured, neither does that have to be infinite, strangely enough. There are very good reasons for holding that the universe must be finite. Aristotle and the medieval cosmologists saw no conflict between a finite universe and Euclidean geometry, right? Because the universe was thought to be contained by a natural substance, although one whose material is not like the material here down here below the Earth. So that's the idea of the outer sphere, the prima overlay, right? A material thing that contains everything. Unfortunately, we can't think that anymore. Too bad. It's gone. The universe, anyway, that we have is both flat and finite. However, it does seem to conflict with the cosmological principle, because you think about it, it has the edge of some sort, you get close to the edge. Presumably things might all look the same in every direction. But unlike the case of a positively curved finite manifold, that's the idea that space curves back in on itself like a sphere. A flat finite space must have a two-dimensional surface, and so not all places within it would be alike. So you want to see. And the ancients had a horror vacuum, a horror of the vacuum, right? So moderns seem to have a horror of being special, right? One wonders if our horror isn't as questionable as theirs. Maybe we really are special. Anyway, a balloon that's above the ground in absence of wind is pressed in all directions equally by air, right? Yet the atmosphere is not really homogeneous and isotropic. It just looks like that as long as it's not very large. It stays away from the edge, right? The edge of the atmosphere. Our visible universe certainly looks homogeneous and isotropic on a large scale. We cannot really say what the whole universe is like. I do not think that reason requires one to suppose that the universe has throughout it a flat geometry, just because the visible universe seems to. If there really is something like an edge beyond which somewhere beyond our sight, even in principle, it would be any observers near that edge that would be special, not us, so don't worry, okay? Our vantage point will be mediocre, so shouldn't fear anything like that. But anyway, there is a kind of difficulty with figuring out how a flat Euclidean universe would have an edge. I see that. Unless you have the outer sphere. Another apparent difficulty for accepting a finite flat universe arises from a confusion between the mathematical and the physical. We cannot infer from our inability to imagine Euclidean space going on forever that the world itself is like that. If matter and radiation are finite, so also is space in the physical sense. Because if there's no matter and radiation somewhere, there's no space. Cosmologists have no trouble in agreeing with Aristotle that outside, if you have a finite universe, outside it, there might be absolutely nothing at all. Right? Aristotle said something like that in the show. No space, no time. There's nothing outside the primordial. So, even mathematically, it's possible for a manifold, a minus of dimensionality to be flat and finite while not being the imaginable space of Euclid. So, because flat has a somewhat peculiar meaning to the mathematician here. A manifold, or by which I mean it gets a dimensional extension, is flat if it can be flattened without tearing it or overlapping it. So imagine a piece of string laid out in a curve, right? Now straighten it out, ignoring its thickness. A string model is a one-dimensional flat manifold, however it's laid out. A piece of paper models a two-dimensional flat manifold, however it may be bent or even crumpled up. It may even be rolled into a cylinder without ceasing to be flat in the sense we are using it as such. So it has essentially Euclidean sort of geometry, is what I'm saying. But if you did do that with with something that's flat in its sense and you curve it like this, if you had an ant crawling along it, right, in any direction unless it's parallel to the axis, it'll be going straight ahead all the time, but it'll come back to exactly where it was before, right? It'll just circle around. So it's possible for the motions that have to be finite to close in on themselves, even though the space has this Euclidean character of being flat. Okay, so if, as I think, an actual infinity of space and matter makes no sense, I'm not maybe prepared to prove that to you right now, but I don't think it makes any sense. I'm not thereby required to reject the flatness of space, is what I'm saying, the validity of Euclidean geometry, because it could be something analogous to this paper curve and while remaining flat. Okay, that's all I want to say about space right now. But again, one thing I want to reiterate is that this idea of the cosmos as a unified thing, space is something real, right? Even though it's not real in the way its substance is real exactly. But it doesn't have the kind of properties that normal substances have. allows us once again to think of the cosmos as one thing, as a unified being, and not just endless space, mostly void, with things scattered around it. Okay, so I think that's some real progress in understanding it. Now, I'm going to turn to time briefly, got a little bit of time left, so we'll talk about this part I'm calling time, more questions and answers. We already had questions and answers. Here's some more. So here's the first one. Is it meaningful to assign an age to the universe? In the theory of relativity, measures of space and time are the relative things, as you know when you studied it. Clocks run at different rates for different observers, either due to the relative motions or due to the presence of variable gravitational fields. Does the idea of a cosmic time make sense in this context? A cosmologist Herman Bondi wrote, quote, although the existence of such a time seems in some way to be opposed to the generality which forms the very basis of the general theory of relativity, the development of a relativistic cosmology is impossible without such an assumption. Right? So that he thinks that you have to have an idea of cosmic time to really develop this map or this model of the universe as a whole. So, speaking of such a time, bonding means not just a time that is an independent reality, but is also a preferred time that has real significance for the universe as a whole. To hold that there is such a time is to hold that there are preferred observers. Since it is a leading idea of the general theory of relativity that all reference frames are equivalent for the formulations of laws of physics, one might think that no reference frames can have priority over any others. But this is incorrect in the context of cosmology. Those observers who are at rest with respect to the universe as a whole will be able to give the simplest and truest possible description of it. Just like if you're at rest in this room, you can give the least distorted account of where things are and what they're doing than if you're running rapidly through it. Right? You couldn't give an accurate account. So the observers who are at rest with respect to the whole universe have a kind of preferred position for talking about it. And relativistic cosmology is consistent with the existence of such observers, and they're called co-moving observers. For they move only with what's called the Hubble flow, that general. You imagine a grid that's painted on a balloon, right? And observers are located at all the intersection points of the grid. The balloon is inflated or deflated. These will keep their relative positions on the surface. This is the defining characteristic of co-moving observers. It is assumed in the theory that these observers will see the cosmos on a sufficiently large scale as isotropically homogeneous. Non-co-moving observers will see a greater or lesser deviation from these symmetries according to how fast they are moving with respect to the co-moving observers. So like when you run through the room, you start seeing some distortion. Since it is posited as a first principle that the universe really has these symmetries, these observers may be regarded as privileged in comparison to others, for they see the whole cosmos in this respect as it really is. Moreover, all observers in co-moving reference frames who see identical physical conditions for a given for a given event in the universe are said to share the same epoch and share common universal time. This is the proper time of the cosmos as a whole, and the current epoch of the cosmos is its present age. That's my point. Physics gives indirect support to this idea that there is a preferred time that many, if not all things, participate in. And here's a quote from a cosmologist. Quote, it is a remarkable feature of our universe that clocks reading electron, proton, and gravitational time appear to remain synchronous, in the quotation. These measures of time are based upon units determined by the electron mass, the proton mass, and the gravitational constant, respectively. They're all different. The unit of time, and the fact that they synchronize with each other, even though they're very different ways of measuring time. I think that's a strong sign that there really is a preferred measure of time in the cosmos. Now, there's reason to think that we are approximately co-moving observers. The fact that the cosmos looks nearly homogeneous to us is one sign of that. And this has been verified by recent observations made from space. Also, our motion is very slow compared to the expansion, the Hubble flow. This means that if we take the results of our measurements as representing pretty accurately the results that would be obtained by an observer at rest in the whole thing, that we can take our results that way. So, using the best current value for the Hubble constant, well, maybe it's revised, but right now when I wrote this, we can infer that the Big Bang occurred about 13.8 billion years ago, okay? And that's in reasonably good agreement with estimates made from other methods. That's a long time ago. So, for the philosopher, the question of whether the unity of time can be grounded in the expansion of the cosmos is an interesting one. This is a good example of a question of interest to the natural philosopher, but not to the physicist as such. So he doesn't really, the cosmologist isn't really concerned with the unity of time as such, but the natural philosopher certainly is their soul is. Yet it does touch upon, this thing does touch upon matters that do concern the cosmologist. If the universe as one mobile being were expanding in a uniform manner, it would seem to be a plausible suggestion. Assuming that natural units can be established without periodic returns, we would have all we need to update Aristotle's account of time as a measure of the motion of the fixed stars. Okay? So in other words, you've got the one time, you've got all these different kind of clocks that can be synchronized, so they're all keeping this time. Those actually give us our periodic returns, right, whenever you have a clock. So that would be great. That'd be great. But unfortunately, there's some difficulties with the idea. If the rate of expansion is increasing with time, as recent data from redshifts indicate, this is where the dark energy stuff comes in. If that's true, there must be some prior timekeeper by which this motion is judged to be accelerating, right? I mean, if you say it's speeding up, you have to have some standard to judge that by. This timekeeper is light, all right? Some motion has to be postulated as uniform, and light seems a very suitable candidate. The idea that light is the primary timekeeper is intriguing, though it has the consequence that beings other than light, including the universe as a whole, do not participate perfectly in time. And it seems to imply that the primary timekeeper is many rather than one, because there are many beings of light. Since light seems to have been the first thing to exist in the natural world, not just in the perhaps metaphorical sense as St. Augustine takes it, let there be light is referring to the angels, but it would even seem to be true naturally that light is the first being. This light, all the many light beings may even be considered to be one in some way. We can talk about that some more if you want. I have an idea about how that might be said. On the other hand, maybe the expansion is uniform, and all this business about dark energy is just wrong, right? I think it's not certain enough to pin all our thoughts on it. There may even be some evidence from astronomical observations that light does move faster as time goes on. That's controversial. This would give rise to the appearance. If that's true, it would give rise to the appearance that the expansion of the universe is accelerating, but it wouldn't be true. You say about light, about the measure. So attributing the unity of time to the expansion of the universe rather than to the motion of light seems to have the advantage that the former posits a single unified mobile, while the latter posits many mobiles, again, many beings of light. But the comparison is not as obvious as it sounds. Even if the universe is a unified whole, it does not follow that its motion is one, or that is a suitable measure of our time. I don't know how to answer this for sure. It's not even clear that what is happening to the universe is even motion, so to speak. You can say more about that if you want. Certainly not local motion. Okay. So those are questions about light. There are questions about time. We don't have at least, I don't know anybody who still can believe that there's an outer sphere that's rotating uniformly. So if there is going to be a unity of time, we have to ground it somewhere else. And I'm just proposing that one way of doing it possibly is to ground it in the expansion of the cosmos as a whole. I'm not asserting that I know that for sure, but it seems to be a real possibility. Okay, now, expansion. I've already indicated that the cosmic expansion is not a local motion. I want to say more about that. Some arguments show, I think, that it cannot be. Local motion is change of place, right? There could be no local motion if there's no place not occupied by the mobile in which it is able to enter. So if it's all space, it can't be moving locally into some other space which doesn't even exist, right? There are no places outside the universe as a whole. There just aren't. It might even be argued that since the universe is not in a place, nor is it anywhere, it is not even the kind of thing that could be thought of as locally moving, even as a whole. So if the cosmos is moving with some other motion, the two possibilities would be that it is altering or that it is growing. Okay, that makes sense? It's hard to see what growth might mean in the absence of something analogous to food to fuel the growth, although maybe this dark energy might give you a way of doing that. So I think, though, it's more likely to think of the expansion of the universe as a kind of alteration of it. But that's, again, subject to more thought with regard to dark energy, because if something is being input into it, you might say it's like a man But the other possibility, again, is that it's some kind of alteration. This seems to fit the way the expansion is described in the mathematics. A scale factor is posited to measure the ratio of the distances between the galaxies to the wavelength of light that's used to measure. So what does it mean to say they're so far apart in ratio to the wavelength of the light? So that's how you measure it. That's analogous to the scale of an ordinary map, right? Because in the map, this inch represents a mile or whatever, right? So mathematical models of the cosmos are contrived to predict the scale factor function, how that scale factor changes from observations. Now, ratios are quantitative relations, but they may describe qualitative relations in as much as these are known to us through measurement, right? Like the expansion of mercury measuring temperature. It may be that that's what's involved here. Perhaps we are seeing the results of alteration either in the measured or in the measure, again in the universe or in the light that's used to measure. If the universe, that's the measure that's altering, we're back to the same kind of difficulty we have with growth. If you're willing to give up the cosmological principle, that everything's the same everywhere, we might posit that there's some disequilibrium in the whole universe which is being adjusted by an alteration of the visible universe, or perhaps by rearranging the mass and the energy in it. We would then need to understand why the visible universe looks so homogeneous. If the measuring tool, that is the light, is the thing that is changing in the requisite way, we have not any explanation at hand of why it should. Why should it change? So, as you can see, I have a lot of questions, but not many answers. It's not at all clear what is going on with the universe, but it is clear that cosmology is in a very preliminary provisional state of development. Beyond certain fundamental issues in relativity and quantum mechanics, before they're sorted out, the story told by the cosmologists should be held with considerable fear of error on those grounds alone. In other words, relativity and quantum theory don't fit together perfectly, and that's a problem. Other things like non-locality complicate the picture. It's very hard to know how to answer these questions from within the science. So we might say, why then should the natural philosophy be concerned with modern cosmological theories? Except maybe for polemical reasons. It seems to me there are at least two good reasons to be involved in the discussion of these issues. First, because clearing away impossible ideas helps in an incidental way for the search for understanding. You rule things out, that's good. Second, because some of the ideas incorporated into the theory are most likely true, and a little truth about difficult matters is always worth having, even in the form of conjecture. We can learn from modern cosmology that some previous ideas about the universe are false, even if we do not have complete certainty about which better ideas we should use to replace them. So, as far as theories within the specialized sciences go, there's no going back. When a new explanation replaces an old one, it is never just a reoccurrence of an abandoned one. Even if it incorporates something from an abandoned theory, the old is modified, no longer just what it was. As when in a Mozart symphony, the thematic material is modulated to a new key. Analogous to elastic waves in Maxwell's theory of electromagnetic radiation. So in other cases, the old is incorporated into the new as a limiting case. So Newton's theory of gravity is a limiting case of relativity. The old cosmologies, either those of the ancients or of Newton, will not reoccur in their original forms as a standard model to be adopted in new research, or perhaps, even adopted to be abandoned. They're not going to come back, in other words. The case is different for the solid conclusions of natural philosophy, as these rest on common experience and not on ever-expanding and improving empirical evidence. Whatever the cosmologists bring forth, as new ideas emerge in the underlying physics or new phenomena come to light, the natural philosopher stands ready to examine the results in light of solid principles. Okay. So here's a little conclusion. The end. There is no agreement at present as to the future trajectory of the cosmos, what it will be. Various models make various predictions, some with colorful names, such as the Big Rip and the Big Messy Crunch. One thing seems clear, though. The far future is not pretty. The cosmos, which is the ultimate closed system, is subject to the second law of thermodynamics. Clausius was roughly on the right track when he predicted what he called the heat death of the universe. Okay? This is the ultimate loss of information in the universe. Even if expansion was reversed and contraction began, the energy in the universe would continue to pass into more and more degraded forms. Predictions of exactly what the cosmos would look like in its final equilibrium state are far from certain. It's hard to imagine that it would be beautiful and interesting. So, let me say a word here then, at the end, not as a philosopher, nor as a scientist, but as a Catholic. Okay. On most scenarios now accepted as possible, the universe is eternal, at least in the direction of the future. Okay? None of the models contain any cause for the cessation of motion. But neither did the Ptolemaic model accepted by the medieval Christian philosophers contain within itself any cause why the heavenly motions should cease, right? But this does not mean that they will not. As the coming into being of the universe is mysterious, so will be its ending. Unlike the cosmos of the Greeks, our cosmos seems to be tending somewhere to a state where there's no place for us. Life cannot persist when the material conditions necessary to support it are gone. And the universe would of its nature become uninhabitable long before it reaches its maximum entropic state. But the persistence of inorganic life, the inorganic material, after life and intelligence have disappeared, would surely be unfitting. Until then, why should not the universe continue on its potentially never-ending course until the trumpet shall sound, the dead be raised, and a new heaven and earth be brought into being? For our Lord says that it will be in the last days as it was in the days of Noah. They ate, they drank, they married, they were given in marriage until the day when Noah entered the ark. So, the end will come when God wills it.